What's up, guys? It's Mr. Bringle, and today we're going to continue working on our constant velocity math practice problems. Previously, we've gone through the example problems that were done in class together, which were numbers 1, 2, and 5. Today, we will be working on problems 3, 4, and 6. So we'll jump right into it here. We already know our process for how to get points, so make sure that you're using that and following along. I demonstrate the exact way that you should be doing it on your paper. This says Jamaica's car is parked negative 20 meters from her house. Be careful about that negative sign right there. She is headed to her friend's house way down the street. Jamaica must go by her own house, which is at a position of 0 meters, and then continue to her friend's house. If she drives for 800 seconds at 20 meters per second, at what position is her friend's house? Okay, so this is one where it's great to draw a diagram here. So let's start by drawing Jamaica's house, right? I'm going to put a J on it for Jamaica. Here's the house. And this is 0 meters, right? It told us that her house was at 0 meters, but it says that she parks her car at a position of negative 20 meters from her house. Okay, so that means that she is going to drive this way, go past her house, which it says that she has to do, and then she goes down the road to her friend's house, which we will say is like right here. F for friend, okay? And then what it's wanting us to solve for is what position is that at right there. Okay, so let's go ahead and write down the things that we were told. We were told Jamaica's initial position, which was negative 20 meters. Make sure you keep that negative in the forefront of your mind. The final position that she ends up is what we're solving for. We need that value. That is this right here. Okay. It then tells us that she drives for 800 seconds. The unit of seconds goes with time. And then it says that she moves at 20 meters per second, and the unit of meters per second would go with speed or velocity. In this case, Jamaica's moving in a straight line, or it implies she's moving in a straight line, and so it doesn't really matter speed or velocity. It's going to be the same thing because distance and displacement would be the same if you're moving in a straight line. So we'll go ahead and write those down. Now, since I need to solve for final position, I obviously need to pick an equation that has final position in it. And so that's going to be one of the equations that involves displacement, delta x. And remember that delta x, the displacement of an object, is equal to the final position of that object minus the initial position. So since we have both of those things, final and initial, you're always going to want to look for xf and xi. Okay, so the equation that works best for this is already rearranged for final position, and it turns out it's that same equation that we pulled off of the position versus time graph when we did our buggy lab and our chase lab. Okay, so we have the final position of Jamaica is going to be equal to her speed multiplied by her time plus her initial position. So now we can go ahead and plug numbers in here. The speed is 20 meters per second. We need to multiply that by 800 seconds of time. And then we're going to add her initial position. Now, her initial position is a negative number, so you can either write this as plus negative 20 meters, something like that. Or if you recognize that that is a negative number, you could just say minus 20 meters. So the key here is to understand that while Jamaica moves for 800 seconds at 20 meters per second, we have to account for the fact that she did not start at 0 meters. She starts behind the finish line. So her final position relative to her house is not simply going to be 20 times 800. So I'm going to break this down into one extra step here, but 20 times 800 is going to be 16,000. And if we're looking at units and how these You don't have to put your units in while you're showing your work, but you can see that this second is going to cancel with this one here. And so that's going to be 16,000 meters, and then we still have this minus 20 meters here. So ultimately, her final position is 15,980 meters from her own house. How far did Jamaica actually move? She moved 16,000 meters, but because she started at negative 20, her final position is 15,980. Hopefully that makes sense. Let's go ahead and move on here to number 4. We previously did number 5. This one says that while building the tunnel under the French Channel Déjà Vu, the drill operator moves at a pace of 1.23 meters per second for 3,623 seconds. What is the displacement of the drill at the end of the dig that day? So it has given us, it's asking us, wait for the bell. It's asking us to solve for displacement. Okay, so displacement, I'm just going to write it in down here, is delta x. All right, and if we're talking displacement, that means technically what it gave us here with the time of 3,623 seconds is a velocity, okay, of 1.23 meters per second. Now, it's going to work out. Again, many of these problems, the object is moving in a straight line. So really, distance and displacement are the same, and speed and velocity are the same. So if you end up using a different equation, it doesn't really matter because, like, if you use speed equals distance over time, it's really not wrong because the object's moving in a straight line, okay? Now, we'll go ahead and use what we're supposed to, though. Velocity is equal to displacement over time. And remember, if delta t is written in here, it just means the change in time. Once again, I don't care if you put the numbers in and then rearrange the equation or rearrange it up front. But I'm going to go ahead and plug them in. So 1.23 meters per second is equal to the displacement divided by 3,623 seconds. So we can see here that what we're going to need to do is we are going to need to multiply by 3,623 seconds on this side and 3,623 seconds on this side. So these will cancel here, and then you're going to have this second and this second cancel. So we're going to end up with units of meters here, and ultimately this equation ends up being delta x is equal to v times t, right? And so when we do that and take 3,623 multiplied by 1.23, we find that the displacement of the drill is 4,456.29 meters. Technically, we should go to about 3 sig figs here is really what we should do. So that would take us to 4,450. We'll go ahead and we'll just leave it at 4,456 meters. Okay. While we want to be conscious of sig figs, I'm not going to be a huge stickler on it. I would like you to consider it, though. Last problem for today is number 6. Now, this is what I refer to as an echo problem, which is very similar to the reflection or echo problem that we did on our example problems, which was number 5 here with the reflecting panels. So you might review that problem real quick before we start this one. Otherwise, it says Hans stands at the rim of the Grand Canyon and yodels down to the bottom. He hears his yodel echo back from the canyon floor 5.2 seconds later. Assume that the speed of sound in air is 340 meters per second, which it is. Room temperature. How deep is the canyon at this location? Okay, so some of these, it's just best to kind of draw yourself a diagram. And here is Hans, and he's yodeling, and his voice travels down to the bottom of the Grand Canyon, which would be way further than this, but that's okay. And then it's going to bounce back up, and he's going to hear his own voice. Now, it told us that it takes him 5.2 seconds from the time that he yells to when he hears his voice. So that is not only the time to go down to the bottom of the canyon, but it's also the time to come back up. So really, if we use this time of 5.2 seconds, we are going to end up calculating twice the distance to go down plus the distance to go up. So preemptively, it is best to go ahead and cut that in half. That's what I would advise. And so let's go ahead and write out our known variables here. So we have a time, and I'll just write 1/2 here, equal to 2.6 seconds. It gave us the speed of sound in air, which is 340 meters per second. And then it asks how deep is the canyon. Really, it's asking you for a vertical change in position, basically. But we'll go ahead. Technically, this would be delta y, or the height, but for the purpose of keeping it consistent with our variables and symbols, we'll go ahead and put in delta x, the change in position of his voice, really. So now we choose an equation. Once again, velocity is equal to displacement divided by time. We can plug in 340 meters per second, set that equal to delta x over the time of 2.6 seconds. We then need to multiply by 2.6 seconds on this side to cancel this out. Multiply by 2.6 seconds over here. Seconds and seconds will cancel. We will be left with basically delta x is equal to 340. I'm going to rewrite this just so we're super clear here. Just trying to show all of my work. You don't necessarily have to do this, but this would be v times t, right? So delta x is equal to v times t. And just to be clear, if you had written that as your equation, like if you just wrote this out like this, then I would give you credit for that, okay? Instead of writing it, in the base form like this, okay? But we'll go ahead and take 340, multiply by 2.6, and you will find that the displacement, or rather the height of the Grand Canyon, how deep it is here, is going to come out to be 884 meters. Now again, if you did not cut the time in half, then that distance or that depth would be double. And if you did that, it's okay. You just have to remember to divide it by 2 at the end, which is why I always advocate for cutting the time in half from the get-go so we don't have to worry about that. But that will conclude today's problems, numbers 3, 4, and 6. Thanks for sticking with me, and I hope you learned something today.